So last time we talked about the equipotential surface generated by two wire charge. One in space here and here. If we have a line charge density of minus rho L, and then for this one you have a line charge density of rho L. Then you choose the origin somewhere in between. So you have a separation from here to here called B, and you have a separation of this line charge to the origin called also B. And in space, you can create some equipotential surface. Say for this one, you can produce an equipotential surface because the whole thing is symmetric above this line. So you can also produce an equipotential surface somewhere here. And in fact, there's a family of curves like this, okay? And for every equipotential surface, there's a center associated with it. And there's a radius A. The center from this circle to the origin is called C, okay? And the radius is called A. For this particular case, you might want to label it as C2, A2, and for this case, well, let's start from 1, C1, A1. And for this one, it's also an equipotential surface, but having a different radius. So let's identify the center of the circle at this location. So from here to here, you have a distance of C2, and let's see, right. And from here to here, you have a distance of A2. And it turns out that there's a relationship between A, B, C. You have C1 square equal to A1 square plus B square. And C2 square equal to A2 square plus B square. Okay, this is the relationship we derived last time, right here. But for different equipotential surface, for different circles, you need to put in different C and different A. But B remains the same. Okay, remember this. B is a constant, right? It's a distance from the line charge to the origin. Okay. So sometimes you need to put in different C, different A, but B remains a constant. All right. And for the electric potential, say at this point, you last time you already derived it. For the electric potential at this point, let's look at this case. For the electric potential on this equipotential surface, you derive an expression that is equal to rho L divided by 2 pi epsilon 0 natural log A over D. Okay, so for this one, you have a potential equal to rho L 2 pi epsilon natural log A over D, but now A is the radius of this one, so you have to put A2 right here. Okay, D is the distance from this line charge to the center of this circle. So it's a distance from here to here. Okay, we call it D. And this D, if you look carefully, this D is going to be equal to what? It's going to be equal to this section plus this section. So this is equal to B plus C2. So let's label this as D2. Okay, so if you want to calculate the potential on this circle, then it's going to be equal to rho L 2 pi epsilon naught natural log A2 D2, that is equal to rho L 2 pi epsilon naught multiplied with natural log A2 what? B plus C2. Okay, this is how you calculate the electric potential on this circle. So you have to take into account the different radius, all right, and also different distance from the origin to the center of the circle. Well, the same thing, let's label this as V2. You can calculate V1, that is equal to, on the right hand side, and the charge reverse is sign. This is plus rho L, and this is minus rho L. So the electric potential on this circle is going to be equal to minus rho L 2 pi epsilon naught natural log A1 over D1. Okay, and A1 is usually, if you have this circle, you know the radius of this circle, which is A1. So A1 is known parameter. This is equal to minus rho L 2 pi epsilon naught natural log A1 D1 now is the distance between this line charge to the center of this circle. Okay, so it's this distance from this line charge to the center of this circle. The center of this circle is right here. So this is the summation of the distance of this one and this one. This one is B. This one is C1. So you have B plus C1. Okay. So if you want to figure out, so this is V2, this is V1. If you want to figure out the voltage difference between these two circles, then the V12 is going to be equal to V1 minus V2. Okay, so you do a subtraction of these two voltage, then you get the voltage difference between these two circles. Okay, so this is the general approach to solve the voltage difference between two equipotential surfaces generated by these two line charges. 有没有问题？上个礼拜我们提到要让各位问问题哈，这个但是如何评量你们的期末成绩变成是一个一点点的困难。这个困难在于就是在学期开始的时候，我已经告诉你们最后的这个成绩要怎么评量。中途改变的话呢，有些人会不喜欢，所以呢，我们还是有小考。但是呢，if you ask questions and 问到我们没有时间小考的话呢，我们就不小考。然后呢，你只要问一个问题，或者底下有人回答一个问题，我就帮你做一个标记，帮你期末加分。Okay, so this is the easy way to get a high grade. So and also an encouragement to you to ask questions. All right. So this will be a rule we're going to do for the second half of the semester. 可以吗 ？OK， 这是鼓励各位能够参与这门课。We'll see how it goes. All right. So this is sort of the equipotential surface generated by two line charges, and so we can come back to this problem. Okay. You can come back to this problem. And when you try to solve this problem, you have to identify what is known to you, what is not known to you. When you draw this diagram, well, definitely the radius of this conducting cylinder is known to you, so A is known to you. And when you put this conducting cylinder into the position with respect to a line charge here, then you definitely know the distance between the center of the cylinder and this line charge. So D is also known. Okay, so you have two known variables. What you do not know is where you should put this line charge to create an equipotential surface. So Di is not known to you, and because Di is not known to you, this line charge can be here, can be here, can be on this line, any place. Therefore, you cannot determine where you can put your origin. 你如果不知道这个 image charge 要放在哪里的话呢 you do not know where you want to put your origin. So B and C are also unknown to you. So you have three unknown variables, B, C, D, I. Okay, so you have to create three equations to solve three unknown variables. 小时候学会的 right? 三个变数要三个式子来解。Well, then you pick up the known variables and try to understand the unknown variables. Di is equal to C minus B. Right, C minus B. And D, right here, D is the distance between the line charge and the center of the cylinder. Okay, so right here, B plus C is equal to D. So you have two equations. You still need one more equation, and that one more equation is the C squared equal to A squared plus B squared. Okay, there's a fixed relationship between A, B, C. With these three equations, definitely you can solve the three unknown variables. And I don't need to tell you the detail how you're going to write down to get the BCDI. I'll just give you the final answer for DI. That DI is equal to this, A squared divided by D. Now, once you have this DI, definitely you can look for the solution for C and B. All right, for example, Di is known to you from this expression. Now you can just use two equations to solve for these two variables. 所以 C 跟 B 也会跳出来给你。Okay, 好，then we're interested in knowing the potential on this surface. From this general equation, Vp equal to this. But in fact, you already solved for the V, the electric potential on the surface according to this equation, right? So it's A2 divided by D. And A2 is, in this equation, is just A divided by D. From here to here is known to you. 所以呢，你知道这个最后结果是这个样子。但是 if you want to start from the very beginning, the expression for Vp at any arbitrary point in space. 你如果要从这里开始的话，也可以。R2, R1, you know that the electric potential is a constant on the surface. So why don't you just pick up something easier? Pick up this point, C, and try to write down this expression. Because at point C, 在这个 C 这一点呢 ，R2 呢是我们从 R1 开始看，R2 呢是R1 呢是这一点到这一点的距离 ，R2 是这一点到这一点的距离。All right, let's go back to this configuration. R1 is the distance between the point of interest to the line charge with positive rho L. R2 is the distance between the point of interest and the line charge with minus rho L. OK， 所以呢，这个 R2 会是这一点到这点的距离，这一点到这一点的距离呢是等于 A 减掉 Di. OK, and R1 is the distance from this point to this point. This is plus rho L to this point, and this distance is equal to what? Is equal to say D 从这里到这里是 D minus A. Okay, so from here to here is the D minus A, which is R1. So you have R1 and R2. Okay, for R1, D 减掉 A. Okay, for R2 is A minus DI, but you have a solution for DI right here. So you can calculate the value of this, and it will turn out to be this value, just the same as the equation we wrote down for this example. Okay, so 这些有些数学技巧在里头 but important thing is that you learn to put in the image charge to create the boundary condition in your problem. And then you can solve for electric field and electric potential everywhere in space except some area within the boundary. Okay, 有问题 Yeah. 这些里头包含一些数学技巧在里头 but don't forget the whole purpose is to put some image charge to match the boundary conditions and to simplify the problem. Okay. Well, the situation can be a little bit more complicated. Well, in fact, we already talked about this situation, right? A big circle and small circle, and these two cylinders having equipotential surface at the boundary. That can be created by two line charges. Well, the question is that what would be the say voltage between these two conducting cylinders, or more specifically, we want to solve the capacitance per unit distance. 每单位长度的 capacitance 是多大？所以呢，我们想象这里有一个 image charge 在这地方，这里有一个 image charge 在这地方，然后把这个边界整个拿掉。Okay, 只要这两个 image charge can satisfy these two boundary conditions, then the voltage everywhere in space can be solved, except that the region where inside these boundaries. And actually it has been solved. Okay, 在这里。所以在这里呢，你知道变数是什么？ Well, you know the radius of this, which is A1, which is A2, and the radius of this is A1, and the separation of the two centers is D. What you want to know is where to put in the line charges. 你不知道是这些 line charge 你要放在什么地方。Okay, therefore, the B, C1, C2 are unknowns to you. Okay, B is the distance from the origin to this line charge, or the distance from the origin to this line charge. 那 C 呢是 well, once you put down this line, then you can define C1 and C2. 那这个问题其实解完了，你要求出来就是这个 V1 minus V2. Okay. 所以你看，我们写出这个有三个变数，我们写出三个式子出来。Number one is C1 square equal to B plus A1 square. This is the first equation. And second equation, well, I told you previously that we have one major relationship, that is C square plus B, C square equal to A square plus B square. And we say that the B is always a constant. But for different circles, you have to put in different C and different A. Okay, so this is the case. You put in C1 and A1. For the second expression, you put in C2 and A2. But you also know C that is equal to, D is equal to C1 plus C2. So you have three equations, and you can find these three unknown variables. OK， 小时候都学过了，三个式子解三个变数 ，right？ 那所以呢，这三个可以解出来了。B C1 C2 解出来之后，哇，太好了，你可以放到这个 V1 里头。V1 呢，这里有一个 B C1 在这个地方。V2 呢，你有一个 B C2 在这个地方，两个相减，你就得到它的 voltage difference. So this is a piece of cake to you, right? So easy. We have been writing this on the blackboard. And then This example is a little bit bizarre, but in fact also belongs to the problem we just described. Suppose that you have a conducting cylinder inside a metal pipe, and then you want to find out the capacitance per unit length for this problem. And apparently this is a equipotential surface. This is also equipotential surface, and radius of this is A1, radius of this is A2. Is known, those A1, A2 are known to you, 因为是你放的这个两个管子到里头去。And 你故意把它放偏心，放偏心的话，你当然知道这两个心中间差多少的这个距离叫做 d。那you can also use a line charge to create the boundary condition set forth in this question. By doing this, you put the image charge here minus rho L, and then you put another line charge here rho L, and then try to create this equipotential surface and also this equipotential surface. OK. 那这里头有几个变数在那里，你可以调。最主要是你放这个 minus rho L 的话，中间画一条线下来，你有个 b a constant value, but you have A1, A2 for the radius, and then so you can adjust C1, C2 to satisfy these two equations. Okay. Again, you can write down these two equations. Basically, this is known to you, this is known to you. B is a fixed value. And so you can adjust the location of this image charge. Therefore, B can be changed to satisfy this equation and also this equation at the same time. OK, 所以在这里头呢 C2 minus C1 is equal to capital D. So again, you have three equations to solve three unknown variables. One is B, one is C. B, C1, and C2 are three unknown variables that you can solve. OK, 那所以呢，你可以把这个三个变数都求出来，然后呢 ，again, you have expression. You have an expression for the V on this equipotential surface. 对于这个来讲的话，外头这个 ，OK, you have, say, we call this V2, we call this V1. This is the expression right here. Okay, but now you have V2 equal to 2 pi epsilon naught minus rho L nature log A 2 D2, and then again V1 is equal to minus rho L 2 pi epsilon naught nature log A1 D1, but this D2 is the distance from this line charge to the center of this cylinder. 所以在这里呢，你可以知道这个是 B 加上 C2. This is equal to B plus C2. Right? And this D1 is the distance between this line charge to the center of this circle. That is B plus C1. So the potential between these two conducting surfaces is going to be equal to V1 minus V2. Okay, and B and C2 and C1 are solved from these three equations. So you can write down the capacitance per unit length for this case. And you can sort of feel that how powerful the image charge method is. Method of image charges. You just put some charges with a known solution, and then you satisfy the boundary condition, and then you can just remove a boundary to solve your problem. OK， 所以在这里 v1 v2 两个相减，你就得到这两个的这个 potential。那这些都是在这个圆柱坐标系里头讨论的问题，我们可以看下一个在球坐标系里头的问题。In the spherical coordinate system, you are not going to use a line charge anymore. You're going to use a point charge. Okay, so suppose that you have a ball. It's a metal ball, and this is grounded. So the surface of a metal is an equipotential surface. So you have a spherical equipotential surface with a potential equal to 0. Okay, and you put there's a real charge right here, and you are asked to solve the electric field and electric potential everywhere in space. Okay, outside this ball. Okay, then let's try to put some charge into space to satisfy this boundary. And because of the up-down symmetry in this problem, so you know that if the problem can be solved, then the image charge has to be on this line because of the up-down symmetry in this problem. Okay, so you arbitrarily pick up some point in space, and then try to solve try to match a boundary condition at this on the surface, v equal to 0. And you know the electric potential generated by a single charge, right? So basically, you just sum over the two known solutions with the right distance, Ri from the image charge and R from the real charge. Ri from the image charge and R from the real charge. And then the summation of these two terms has to be equal to 0, according to this boundary condition. This metal ball is grounded, right? So it taught that you have a relationship Ri over R equal to minus Qi over Q, and Qi is something with a fixed value. 我们把这个镜像电荷一放下去的话，这 Qi 就是一个定值， so it's a fixed value. So if this is a fixed value and this is something you put into, this is Q is something you have in the system, then this means Ri over R is constant. Well, if you set Ri equal to R to be a constant, then this problem returns to the problem you have before for a line charge. 在之前的话，我们说最早的时候呢，你看我们有这么一个问题。你看，我们有这个问题，这个问题呢是在这里呢要求 Ri 除以 R 是一个定值，也是 constant. So the same problem. Okay. So whatever solution you derive from this problem, you can take it. So Ri over R is equal to A over D. Okay. So come back, just copy the solution into this problem. Okay, so I over R can be A over D. A is the radius of this circle, and D is the distance from the real charge and the center of the circle. Okay, so this problem is solved. 你得到答案了。I over R is equal to A over D. Then Qi is known, is equal to minus Q multiplied with this factor. So you also solve the value for the image charge. This time, the amount of charge for this image charge is not equal to the actual charge. Okay, 有一个这个 ratio 在这个地方。 Well, if you are curious, you might have asked yourself that what if this is not grounded? 如果说这个球 if this is not grounded, instead this is biased over some voltage. Let's call it V0. And then you have a charge Q on the axis. How would you solve this problem? Well, you can divide this problem into two parts. Number one, this is grounded, and try to find an image charge to give you an equipotential surface on the surface of the ball. And then you can put in another charge to create this V0. In other words, you can put another charge that's called Qi2 that can produce this potential. Okay, so for this problem, you're going to have Qi1 and Qi2. Okay, and Qi2 is very easy to derive because Qi2 basically is equal to 4 pi epsilon naught A. This is radius A, and then this Qi2 is going to give you V0. So this is a simple problem for you to solve, right? So now that you have determined the ratio of Ri over R, and you also determine the ratio of Qi over Q, then you can just sort of remove this boundary and then solve the electric field and electric potential everywhere in this region except the region inside this ball. Okay, 所以呢，这时候呢，整个问题变成就是两个电荷的问题了，不是一个这个蛮复杂的这种边界的问题在那里。Okay, 两个电荷的问题，所以呢 if you want to get the electric potential, you just sum over these two terms with the appropriate charge for the image charge. And then if you want to know the electric field everywhere, just take a gradient of it. Okay, and if you want to know the charge induced on this surface of the ball, then you can calculate the dot product of the surface normal with the displacement vector or the electric flux density, electric field flux D right here to get this surface charge on the surface. Okay. Any question about this image charge problem? 有没有任何问题？镜像电荷的问题有没有任何疑问 ？Okay. 你如果做一个这个积分 if you do a surface integration for this surface charge on this ball, you tell that it's going to be equal to Qi. Okay. This is sort of the conservation of total charges. 如果做一个积分的话，你会得到这个，就是整个上头的面的这个电荷呢，就是以 Qi 这么大。OK， 有没有问题？所以目前的话，我们学的两招。Number one, you use Poisson's equation or use Laplace equation to get your answer. Okay. If you know the boundary conditions, then you can derive the electric field, electric potential everywhere in space, subject to the Poisson's equation and Laplace equation. The second approach is to use method of images, right? 你在空间里头有一个问题，但是你知道它边界条件。You can just put some charges into some appropriate location to create the same boundary conditions, but you also know the solution for the charge, the electric potential associated with the charge you put into the system. Okay, and then you can sort of just borrow the Coulomb's law to deduce the electric potential right here. 但一刚开始的时候，这个问题看起来还蛮复杂的。You have a charge right here, and you have a metal ball grounded. Okay, a grounded metal ball. 所以呢，你只要把这个边界条件用适当的知道解的电荷把它给建造出来的话呢，你就可以用这个已经知道的解来解出所有的这个电场跟电位的值在空间里头。Okay, and I'm going to tell you a third approach. This third approach is more mathematical. Okay, basically, the Laplace equation will give you some certain sets of solutions. So we can just borrow the known solutions to construct the solution associated with the electric field and electric potential. Okay. 我们来看一下这怎么解。Well, for this Laplace equation, well, if you just treat it as a mathematical expression, just look at it as a mathematical expression. Basically, it's just a differential equation, a partial differential equation. So if you know the boundary conditions, then you can solve the variable described by this differential equation. And some mathematician 一些数学家呢，其实已经帮你找出它的可能的解了。So for this session, we'll just borrow those known solutions and try to match to the boundary conditions, and then find the final solutions for the electric potential. Okay. So very often that there are certain sets of boundary conditions in a given problem. 在之前，我们说我们有这个 conducting cylinder, and we specify the electric potential on the surface to solve the problem. And so number one, we can specify the electric potential on some boundaries, okay, for a given problem. And this is called a Dirichlet problem. And sometimes it's easier to specify the electric field on the surface, okay? And for this class of problem, we call it Newman problem. You specify the normal derivative of the electric potential with respect to the surface normal. Basically, this is, if it's a conducting surface, this is the normal component of the electric field at the boundary. Okay, and so on some problems, in fact, it's a mixture of these two boundary conditions. 有时候呢，在某些边界上头，这里呢是 specify electric potential， 这里呢是 specify the normal component of the electric field. Okay, and so sometimes you have some mixed problems, but the boundary condition have to be specified to solve this Laplace equation. 所以接下来呢是比较数学的部分了，因为数学家帮我们算出它的这个可能的解是什么样子。OK， 然后呢，我们再把这个可能的解拿来设法凑出它的答案出来。Okay, for example, in the XYZ coordinate system, the Laplace equation is expressed by this expression. Okay, double derivative of v with respect to x, and double derivative of v with respect to y, and then the third term is double derivative of v with respect to z. Well, in mathematics, there's a technique to solve for this differential equation. Well, it's called separation of variables. Suppose the solution look like this: it's x as a function of x, a function of y, and a function of z, and the multiplication of these three functions give you the solution. We don't know yet if this is going to solve this Laplace equation or not, but we can just try it. All right, we can just try it. Suppose that the solution look like this, and put this into this expression. 把它放进这个Laplace equation 里头来，然后整理之后呢，你会得到这么一个式子。 Okay, because this is partial derivative, so the first term basically just differentiation of this capital X with respect to little x. And the second term is also the xz multiplied with the ordinary differentiation of capital Y with respect to little y. The same thing here. OK， 我们把它整理一下，把每一项都除以 x, y, z, then you have this expression equal to 0. And this is something actually you have been dealing with in engineering mathematics, right? 右边是等于0，那这里是完全是 x 变数，这里完全是 y 的变数，这里完全是 z 的变数，但是右边呢跟 x, y, z 一点关系都没有。Well, so this means that we can define this is to be a constant value, and this is a constant value, and this is also a constant value, and these three constant values, the summation of these three constant values has to be equal to 0. Okay, so you end up having this kind of three equations with their eigenvalue, the sum of these three eigenvalues equal to 0. Basically, it's some sort of some operator operate on x, and then you have some eigenvalue, this kind of problem. Okay, and this could be positive, negative. 这个以前在公式里头都学过了，轻而易举，对吧？在公式都学过了，所以现在你有3个式子在那个地方，但是呢，这3个式子并不是完全独立的，它们的 eigenvalue 加起来必须等于0。So this is sort of just mathematical. So we can just look at one equation and try to find a general solution from this equation. And that general equation will apply to the rest of the two, except that the summation of the three eigenvalues has to be equal to 0. Okay, so let's just pick up one equation right here and try to find a general solution of it. Okay, number one, a trivial solution is that for these three terms, sum to equal to 0, we can just put 0, 0, 0 right here. So this is a trivial solution. So the first solution is quite trivial. Just put kx equal to 0, and then this x function is going to be a linear function with respect to the variable x. Okay, so let's just first find out all the possible solutions, and then later on you have to match your solution to the boundary conditions. Okay, 那第二个解呢是 what if the kx squared is a value larger than 0? Then you know that the solution is a harmonic function, cosine, sine. Right? 你如果把 sine、cosine 放进来的话呢，这个 kx 大于0的话，那是一个解。And if you prefer to express it as a complex, not a complex exponential, then you can write down the solution of this form. And for this equation, c1, d1 could be complex numbers. Okay, so you can use the Euler's expression, Euler's formula to express this into complex exponential. 这都没问题，以前都学过了。好，现在的 kx 平方如果是小于0的话，那这里头变成虚数的 ，sin 跟 cosine 里头变成虚数的话是什么？是 hyperbolic sine, hyperbolic cosine. But before I show you the third possibility, you have to keep in mind that this is just a mathematical expression. But I told you you have to match the solution to the boundary condition. So you have to sort of think about or imagine the behavior of sine and cosine. Sine 跟 cosine 是什么？它的 behavior 就是一个周期性函数 ，right？ 周期性函数。所以呢，你如果有边界条件，将来呢是周期性函数的话，那它解很可能就是这个解。Okay, so for sine cosine, you have this kind of sinusoidal variation. It's a periodic function. So according to the boundary condition, if you have a boundary condition specify that a periodical variation, then you have to pick up this solution, but not this solution. OK， 你得到一个这个数学式子的时候，你要想象它的这个它的机械性的功能或者是它的物理意义。像这个的话，代表说这个函数呢随着 x 增加或减少。OK， for this solution, you have a periodic function. Okay, for the second solution, then for the third solution, this is less than 0. Then you have sinh and cosh or exponential. 你这个变成0之后呢，你可以把它写成这个 sinh 或 cosh， 因为这里头变成虚数了。Sin cosine, if you have imaginary unit inside sin cosine, then you can convert it into sinh and cosh, hyperbolic sine, hyperbolic cosine. Or you can just spell it out and have this solution. OK， 你知道 sinh 跟 cosh 的这个式子 ，right？ You have a sinh kx. This is 1/2 exponential kx minus exponential minus kx. You have cosh. Then you have 1/2 exponential kx plus exponential k minus kx. Okay, so you can just decompose this sinh and cosh into exponential kx and exponential minus kx and write into this expression. Well, again, when you write down this sinh cosh exponential kx exponential minus kx, you have to know the behavior. You have to know the behavior of each function. Therefore, you know how to pick up the solution to match your boundary condition. For this exponential kx, follow this curve. Okay, there's an important tendency for this curve. When x approaches infinite, this exponential kx is going to go to infinite. So if you have a region, you have to find a solution, and this region includes a point at infinite. You cannot use this solution because the whole value is going to diverge. 你如果再解一个问题，这个问题的这个范围呢，包括无限远的那一点的话，那你不能把这个解拿出来用了，因为这个解呢给你一个无限大的值在无限远，这是对有线电荷来讲的话是不可能的。OK， Instead, you have to include a solution. Follow this curve. At the infinite, this curve goes down to 0, and this is exponential minus kx. OK， 所以有时候呢，你必须把这个解拿掉。你如果包含这个解呢在无限远的地方，但是呢，你如果是包含一个范围是在有限的位置的话，那你可以用这个解。Okay, so this is exponential kx and exponential minus kx. Well, for this sinh, you follow this curve. It's an R function. Number one, it's an R function. 它是一个基函数. And this equation goes through 0 point. So if you have 0 potential somewhere in your boundary, then this could be the solution you want to pick. Okay, there's a 0 at x equal to 0. 你如果有一个边界条件是 x equal to 0, your electric potential has to be equal to 0. Then this is going to be the solution. Okay, but you have to be careful that if this is less than 0 or larger than 0, if you have an eigenvalue larger than 0, then you should pick this solution, sin kx, because when x equal to 0, this sin kx is also 0. OK， 所以你必须小心的选择这个解。那对 cosh 来讲的话呢， you follow this curve. It's an even function. Okay, and when x approaches infinite, its value also approaches infinite. So if you try to figure out the electric potential, including a region at infinite, then you cannot use this solution. Okay, 所以这是这个式子的3个通解在这个地方。那你到底要用哪一个解下来描述你的这个electric potential? It depends on the boundary conditions, and you really need to understand the physical picture of these 3 equations. Therefore, you can pick up the right solution for your problem. OK， 所以下堂课我会告诉你几个例子。